Daniel, and my thanks to all of the organisers of this wonderful conference. I've had email correspondence with several of you, and I'm extremely pleased to be here to help celebrate Charlie's amazing contributions to mathematics. And happy birthday, Charlie. I'm not sure when it is, but have a wonderful year of birthday celebrations, perhaps. I remember that Charlie spent a sabbatical in Perth a long, long time ago. And we had a great time working together, and so we have exactly one joint paper. And so I couldn't really talk about that area. So I've chosen something a little bit different. And I want to tell you the story of my work with Moharam Irad Musa. Moharam, which way is forward? Yes. Moharam visited my university in Perth, Western Australia, on an Endeavour Scholarship for about 5-6 months, way back in 2010. And we've only just got all of our results together and submitted them for publication this year. So I thought I would tell you a little bit about what we were trying to do. We were focusing on the benefits of Cayley digraphs, and we're asking the question whether these extend nicely, naturally, to much larger classes of groups. Of course, we're not the first people to ask these questions, but let me take you through what we were doing. So to remind anyone that may not have known, a Cayley digraph is based on a group G. The vertices are the elements of the group. And we need a subset S of non-identity elements of the group G, and this S determines where the edges go. So if we start with an element G, little g, of the group, we have an edge, a directed edge to another H, if and only if the ratio HG inverse lies in S. So that's the definition, and it will be undirected if S is closed under forming inverses, because that would then give us an edge going back in the other direction. So some of the benefits of Cayley digraphs are that is this sort of local adjacency property, that at any vertex G, you know exactly where the out edges go by forming multiplication in the group. And another way of writing this joining relation was that G is joined to S times G for all of the elements S in the set capital S. So that's a good property. It's also got a lot of symmetry, and I love symmetry, which is why I've often worked on Cayley graphs. That all of Cayley graphs are vertex transitive, because the right multiplication action by multiplying the elements of the group G obviously take these sorts of out edges to other out edges, and this tells us that the group G is acting actually regularly as a group of automorphisms. So all of these Cayley digraphs are vertex transitive, and there are many nice Cayley digraphs, but lots of vertex transitive graphs are not, and we were using this smallest vertex transitive graph that is not a Cayley digraph as a test. So the Peterson graph, this Peterson graph is not a Cayley digraph, and we wanted to expand this set, so we would at least include the Peterson graph in our class. So we were willing to consider trade-offs. We really wanted to keep this local adjacency property. We didn't much care about the regularity or the symmetry. And we were looking for a larger graph family that contains at least all the vertex transitive graphs, and especially that contains this one. The local adjacency is quite useful in many applications where Cayley digraphs are used, because they're often used for interconnection networks where you can just map out where your routing is going locally, vertex by vertex, as you move out. So, this is a picture of Moharam. He was actually thinking that he might try and get here, but obviously he wasn't able to. So, lots of people have asked questions about generalizing Cayley digraphs. I might run through a few of these just to give you the context of where what we were doing lies. So way back, many years ago, 69, 74, two independent papers, Tay and Dorfler, substituted, instead of a group, they substituted a quasi-group, used the same definition, and they talked about quasi-group digraphs. So what's a quasi-group? Well, it's a set. You can multiply its elements, and for all elements A and B in this set, in the quasi-group, the equations AX equals B and YA equals B have unique solutions. So that forms a quasi-group. I don't know a whole lot about quasi-groups, but what these people proved was that every finite regular digraph is a quasi-group digraph. So you might say, well, that's the answer, isn't it? You've got all possible regular digraphs arising as quasi-group digraphs. But we don't know very much about quasi-groups. We can't work with them very well, so we wanted to explore this question a bit more. Other people have looked at it. For example, this was like about the 70s, so 20, 30 years later, Jeanette Digraphs again looks at quasi-group digraphs and puts many, many extra conditions on them and calls her class of graphs, she calls them quasi-Cayley graphs. But she puts so many extra conditions that her quasi-Cayley graphs they're all undirected and they're all vertex transitive, but not all vertex transitive graphs are quasi-Cayley graphs. So we think that maybe her class of quasi-Cayley graphs is a bit too small. It certainly contains all the Cayley graphs, but maybe too small for us. Something which I'll come back to because this is the one we really landed on. 1990, a beautiful paper of Alex Steinbaum / Rosenberg introduced a class of group action digraphs. Group action, GA. And here you don't need a group, you need a set. Even though the name says group action digraphs, you start with a set X and a set of permutations of X. And the GA digraph here, it has more or less the same definition. So the vertices are the elements of X. You take a vertex X and you join it with an arc to the images of X under the permutations in the set capital S. And you label that arc by the element little s. So you might have many arcs, even to the same vertex, with labels on all of the arcs. So it's not a simple diagram that they're drawing, but this is their group action diagrams. And numbers of people, so this is 1990, I'll come back to their work a bit later on, but numbers of people, again, put on many extra conditions to the group action diagrams. And there are two papers I will mention, both of them published in 2002, so it's about 10 years after the Einstein et al. Work. Pizanski, Tucker, Digraphs. They put extra conditions on their graphs and they call them action graphs. They're interested in self-inverse, inverse closed subsets of permutations. And they're interested in interpreting certain symmetry properties of graphs in terms of conditions on the action graphs. So they've got a particular interest in application in their work. And another paper, same year, Sandy Knowledge, he studies something which again he calls action graphs, but that has a different data structure. So it's rather like a GA graph, but it allows some semi-edges, and again, he had a different motivation. He wanted to gain insights into covering projections on graphs and what this says about embedding graphs as maps in surfaces. And people work on other things. They substituted a groupoid for a group, or a semi-group for a group. There's many papers in the literature about this. And if we return to groups, then there's another paper, 1992, just after Einstein's paper, where you'll find something called a generalized Cayley graph. And that's kind of interesting, again, with a particular motivation. It feels like they're defining a Cayley graph, except the joining rule has a little bit of a twist in it. Their motivation was that they wanted to look at the standard bipartite double of a graph. So let me explain what that is. So you start off with a graph, and gosh, I've called the whole graph X here because they do. You start with your graph, you take 2 copies of the vertex set of the graph. And on the left, you put subscript 1 on those vertices, and on the right, you put subscript 2 on the vertices. And whenever there is an edge between an X and a Y in X, you will put in this bipart double an edge between an X1 and a Y2. And so what they were trying to do was to understand when the double was a Cayley graph. And so they proved that this double of X is a Cayley graph if and only if X was one of their generalized Cayley graphs. So again, they had a particular purpose in their extension of the notion of Cayley graphs. And again, all of their examples of vertex transitive, but not all vertex transitive graphs arise. We very much hoped that our larger class of graphs would at least contain all of the vertex transitive graphs, because at least we wanted the Peterson graph to be there. So we tried a few things. And the first thing we tried, it's already been published 2016, and it's not the derangement, so I'm not even at my title yet. The first thing we tried was to change to keep with the group. The vertex set's going to be a group, but start with joining set being split up into 2. So we're going to have a left set and a right set, L and R. They're both subsets of the group. And we will have an arc, an edge going from X to Y, if and only if I could write Y as X, multiplying on the left by L inverse the right by R, where L is in the left set, R is in the right set. And this class clearly contains all of the Cayley graphs. You could take one of these sets for the identity and the other one to feel like the S of a Cayley graph. It's much, much larger from the Cayley graphs. And it took us a long time to work out whether or not we had captured the Peterson graph, and we actually found out, no, we had not. So even though this looks a little bit different, it does, the Peterson graph is not one of these 2-sided group digraphs that we call. Actually, that wasn't our name for them, but a very enthusiastic referee strongly suggested that we change our name into this. So we call them now 2-sided group digraphs. So we failed. We didn't contain the Peterson graph. It does have this nice property of local adjacency. You can tell where all the out edges from X are going. It contains some rather extraordinary examples, and I always think, when I look at this, I think, that's amazing. This is one of these 2-sided group digraphs. It comes from the dihedral group with 12 elements, with a rotation A that rotates you around sort of 6th of the way around, and a reflection B, so the dihedral group. If you take this set L is size 3 and R is size 1, this is what you get. You have these 12 vertices. One component has got size 8, the other component is this complete graph of size 4. So obviously this graph is not vertex transitive, right? Nothing like it. And notice what I'm doing already. Oops, I should get out the shadow. Whenever I have an arc going in both directions, I don't bother drawing the two edges. I'll just collapse it down to a single undirected edge. So this is an example. What did we learn about these graphs? Well, we found some necessary and sufficient conditions on L and R for our 2S graphs to be undirected and regular of valency, what you would hope it would be, so the maximum possible size of L times the size of R. And this is an example. This graph I've got down here has that property. It's undirected, it's regular of valency 3 times 1. Still open question, we've got no idea, no one's answered it yet. Is it possible for one of these 2-sided group digraphs to be undirected and regular, but valency smaller than the size of L times the size of R? Don't know. But we asked several questions. One question that we asked was, can the outvalency, the number of outneighbours of a vertex, be constant, but the invalency be non-constant? And a group of young mathematicians in the US answered that and said, yeah, that's possible. And they gave another example, again with just 12 vertices, but based on the group A4, the alternating group A4. They drew it, but I didn't picture it here because it's a real mess. I can't actually see what's going on. There's so many arrows in their picture, and I'm going to draw it myself. So some things are known and some things are not known. But it brings me to the topic of the talk. We still haven't got a set of graphs that contain the Peterson graph. So we went back to Einstein, Bonslag, Rosenberg construction of the group action digraphs. Now if you think about what's going on here, if one of these permutations in S has a fixed point, x, fixes, so x to the S is equal to x, then you're going to get a loop in their group digraphs. We really didn't want loops, so we can avoid having loops by requiring that every S is fixed point free or a derangement. So we're going to decide we'll restrict to loopless group action digraphs, which says we're going to ask that this joining set S consists of derangements. Okay, first step. The next step is that, of course, in the group action digraphs, you can have two or more arcs going from X to Y if you happen to have different permutations, S and S dash, in your set, and both of them take X to Y. And in the group action digraph, you would label one of the arcs S and one of the arcs S dash. So you could maybe talk about the multiplicity of xy as being the number of arcs from X to Y. Maybe it's 0, maybe it's 1, maybe it's something else. You might decide to restrict further and ask that all of these multiplicities should be at most 1, and then you would get the multiplicity-free group action digraph. But that really seemed too small a class. So instead of that, we decided to ignore arc multiplicities. And so we defined, eventually, here's my definition, a group action digraph as the underlying simple digraph of one of the GA graphs. Remember, we're going to take S to consist of derangements, so no loops ever. But we'll think of the arc set as the pairs X and the image of X under S, or different permutations S, points X. And we're thinking of that as just a set of ordered pairs of distinct vertices. So we're just going to think of these as simple digraphs. That's our derangement action digraphs. So what do we know about them? Okay. Well, because we've forgotten things, then of course certain things are not unique. So here's the tiniest example to explain some of the non-uniqueness. You could get exactly the same derangement action digraph for different S's. Let me take X to be the set of points 1, 2, 3, 4. And I'm going to get this graph up here, this cycle. And again, when I get two arcs, I just draw an ordinary edge. So if I take S1 to be the two cycles, 1, 2, 3, 4, and 1, 4, 3, 2, I will get that graph, right? Or if I take S2 to be these two double transpositions, the first one, 1, 2, 3, 4, will give me the horizontal edges, and the second one will give me the two vertical edges. And so those sets have got nothing to do with each other, but they give me the same graph. So that can happen. We don't care. That can happen. Turns out this is multiplicity free. You definitely won't always be able to even change around the subset S in general to get a multiplicity-free example. And so I'll just get one more simple example here. If we take now X to have these 8 points, and I take the set of permutations has size 3, let me see. If I take the last one, C, which is product of these 4 transpositions, I'm going to get the edges 1, 8, 4, 5, 6, 7, 2, 3. So the horizontal and the vertical ones. If I go back to A, I'll get the other 4, the slopey ones. And then with B, I'm going to pick up this chord. So it's not multiplicity free. You can do a bit of counting. It's not possible to replace S by any other subset to get something that's multiplicity free. And so funny things happen. Okay, let's talk about what we know in general about the structure. Well, you can write down necessary and sufficient conditions for one of our derangement action digraphs to be multiplicity free. And here is a technical condition, and you can prove it by just following your nose. This condition says if you take something in S and multiply it by the inverse of something in S, you either chose the same thing and you get the identity, or you must get a derangement. And insisting that you must get a derangement is equivalent to obtaining a derangement action digraph that is multiplicity free. Turns out that this is also equivalent to the derangement action digraph is regular of valency as large as it could be. I thought that's kind of interesting, but I want to tell you about our first substantial result. We proved, and I'd like to explain a little bit of how we did it, because I think I forgot to mention that we would love if our work applied to possibly infinite digraphs, but I want the set S to be finite, so all the valencies are going to be finite. And some of our work does and some of it doesn't. So here's our first theorem. We can prove that every finite, simple, regular digraph is a DA digraph. How do we prove it? Well, the proof, and this is definitely, we're talking about underlying simple digraphs, definitely with probably edges with directions on them. The proof uses the concept of a perfect matching in a simple undirected graph, and it has an application of Tutt's one-factor theorem, which has to do with matchings in undirected graphs. So let me explain. What is a perfect matching? So a perfect matching in an undirected graph, we'll think of that one as an undirected graph. It's a set M of undirected edges, and every vertex lies at exactly one edge. For example, up here, take the edge 1, 2 and the edge 3, 4. That's a perfect matching. So is 1, 4, 2, 3. And Tutt's one-factor theorem tells you when necessary sufficient conditions for the existence of perfect matchings in these graphs. Well, our theorem's about digraphs, so how do we apply Tutt? Well, we convert our given finite, simple, regular digraph. So here it is, gamma, it's a finite, simple, regular digraph, vertex set X, arc set A. We convert it into an undirected graph in a similar way to the doubling that I just explained before. So for this digraph, we're going to take 2 copies of X, subscript 1 here, subscript 2 over there, and whenever we have an arc, a directed edge from X to Y in our original graph gamma, we will put an edge from X1 to Y2 in our double. Okay, that's our doubled graph. So what do we do? Let me show you this picture. Here is an example. This is a finite, regular, simple digraph, outbalancing 1. And if I do what I said before, I have an arc 1, 2, so I get an edge from 1 sub 1 to 2 sub 2. The arc 2, 3 gives me an edge 2 sub 1 to 3 sub 2. And the arc 3, 1 gives me an edge from 3 sub 1 to 1 sub 2. So that's my doubled graph. It's undirected. It's also bipartite. Actually, Tutt's theorem, or a consequence of it, says that every bipartite undirected regular graph has a perfect matching. So in fact this one is a matching, so I don't have much to choose from. So in general I will choose a perfect matching. Here I've got a perfect matching. From this perfect matching I will define a map from the vertex set X to itself. So here is my definition. Walk up here. Take the point 1. I look at my doubled graph, at my matching, and I see that 1 sub 1 is joined to 2 sub 2. So in my map I take 1 to go to 2. Then I look at 2 sub 1 and I find its edge in the matching. It goes to 3 sub 2, so I map 2 to 3. I look at 3 sub 1, find its edge. It goes to 1 sub 2, so 3 goes to 1. So I define this map in general for the matching in my graph. It's always well defined, yep, because I've got a matching. It's always fixed point free because I had constructed this double graph from a simple digraph. So if I have an edge from an x to a y, the x and the y are different. So this is a derangement. It's actually a derangement. Fantastic. And also, if I run through the vertices of x and I look at x and the image of x under S, it's going to be a bit like this. The way I define gamma is that that's an arc of my original graph gamma. So I apply Tutt, find the matching, define S, it's a derangement, and all of these pairs are arcs. So the next thing I do is I remove all those arcs, and for every vertex x there was exactly one out neighbour that I've taken away. So I get left with a finite, simple, regular digraph, valency 1 less. And I do the same thing over and over and over again. If I start out with valency k, I get k of these derangements. And the way it's all set up, it's absolutely obvious that if I collect together all of those derangements together and call that set capital S, I have exhibited that gamma is precisely the dA derangement action digraph for X with S. Q and D. Most beautiful proof. I would love if someone knew some theory about infinite locally finite graphs that knew when I could expect that an infinite, simple, locally finite regular digraph would have a perfect matching, because if you knew some conditions about this, then you could extend this sort of proof. But I don't know how to do that. Okay, let's move on. Have I got how much time? 10 minutes?
Yes, at least.
Oh, cool. Good. Oh, fantastic. I've got 2 sort of points I want to talk about. Yeah. Okay, what else? So, conditions for these dA graphs to be undirected. Okay, so you can see from the definition, if you take a vertex x, the out neighbours are all of the images of x under the set, elements of the set capital S. And the in neighbours would be, similarly, all the images of x under the inverses of the permutations in S. So the dA graph is undirected if and only if for all x the out neighbours and the in neighbours are the same. And that looks a bit convoluted, but we write it this way, it's precisely correct. It's undirected if and only if this condition holds. Turns out it's undirected and regular of the biggest possible valency if and only if this condition 1 and 2 hold, and this is the condition that I talked about a bit before, the SS inverse has to be a derangement. And again, we do not know conditions for this thing or whether it can be undirected and regular of valency less than S. It's again something that we don't really know much about. A comment about this condition. If S is closed undertaking inverses, then it's much easier to say, well, this is obviously true and we don't have to write it out singly for all of the vertices X. But this condition can hold even if S is not closed under inverses. Let me show you an example. Take the set 1, 2, 3 up to 6. Take S to be this 6 cycle, 1 up to 6. This product of 2, 3 cycles, and this 4 cycle times a 2 cycle. Obviously this is not inverse closed, right? The inverse of a 6 cycle is a 6 cycle, not this one. So turns out that, you can check it, I won't check it, that this condition holds for this subset S, and this is the graph that you get, and this time I have actually put in all of the arcs instead of sort of collapsing them to edges. So yes, this condition can hold without capital S being self-inverse. But there are many, many undirected graphs that can be written as a DA graph with S being self-inverse and this other property holding. And here is our second theorem. This family of graphs, which we can do with S being self-inverse and this other property, includes every finite, regular, simple graph of even valency, every finite, regular, simple graph of odd valency that happens to have a perfect matching, and hence every finite vertex transitive graph and every finite, regular, bipartite simple graph. So in particular, the Peterson graph is a DA graph because it's vertex transitive, because when you draw it, I should have put the picture again, you can see a perfect matching with the spokes coming out, even though it's got odd valency. So definitely we have achieved our Peterson graph, and we've got a family that contains all of the vertex transitive graphs. And, well, we don't actually know of finite, regular, simple graphs which are not there. It's just that these are the ones we proved could be there. And the proof, again, I'm not going to take you through the proof, but I'll just tell you that we use Tutt's one-factor theorem again, and an old theorem of Peterson about the decomposition, his decomposition theorem about when you have a two-regular spanning subgraph in simple graphs. And again, these theorems seem to be only available in what I can find in the literature, because this is not where I'm an expert, for finite graphs. So again, I would love it if someone who works with infinite structures knew a bit more about the existence of perfect matchings or two regular spanning subgraphs in infinite locally finite graphs, because maybe something like this could be extended to give us much more information about the infinite examples. Okay, the last phase of what I want to tell you about is connectivity. Let me show you an example of a very simple example of one of these DA digraphs that is not connected, and explain how easy it is to construct them. So I've got, I'm sorry that I've relabeled this, I really should have labeled this 1, 2, 3, 4, but here I've got a triangle, 1, 2, 3, and a 4 cycle, 4, 5, 6, 7. So if I take actually any, I suppose, any two nice looking graphs that I know how to write, this one and this one, as a DA graph using the same number of derangements for each, I can then write my set S So this 3 cycle, I could get it by taking the cycle 1, 2, 3 and the cycle 1, 3, 2. I could get the 4 cycle by writing 4, 5, 6, 7 and the reverse, 4, 7, 6, 5. And if I just concatenate first one and the second one, I have to get fixed point free elements, so I have to be careful. You can just actually visibly see that we get these 2 as our connected components of this derangement action digraph. You can kind of imagine constructing these very freely, it's a very loose construction. It suggests that the most interesting examples are the connected ones, and that they're the ones we should be looking at and asking, what do we know about them? Let me show you the converse of this. So this says, these ones are easy to construct. It feels like this should always work. Yeah? So what happens in general? Now I'm doing this in a little bit of a complicated way because it does work in the infinite case. So I've got this connectivity relation which everyone uses in digraphs. So I'll say that x is connected to y if there is a directed path that starts with x and finishes with y, and each of these, the I minus 1 to the I, is a directed edge, is an arc in the graph. This connectivity relation is an equivalence relation, surely in all finite digraphs, and also in every DA derangement action digraph, provided that the permutations in capital S, the derangement, have only finite cycles. So I can't deal with it. This is not an equivalence relation if I've got an infinite cycle. So this does apply to